started now, the last session for the day. So it's very happy to have Elisaveta Semenova. She's at the University of Oxford, and she's going to give you a talk on how to sort of put together two really important technologies, the generative models and GPs.
One last question. Is there a way to connect the...
This doesn't work.
This doesn't work, great.
Here.
All right. Okay. So, good afternoon, everyone. Welcome back. I would like first to start by saying big thank you to the organizers. Many years ago, when I was a PhD student, far away in Switzerland, UK looked like a very distant island. I discovered Gaussian process summer school, and for years I've been looking up to it. I was stalking the materials of the summer school. I was trying to go through any materials I could find to learn about Gaussian processes, because there was not much expertise around where I was doing my PhD. So I would like to say you're all extremely lucky to be here. And I could never have imagined to actually attend GPSS and be on this side of the table straight away, rather on that side. So this talk will be about disease mapping and spatial statistics and Gaussian processes, and how actually we would like to get rid of Gaussian processes. I would like to relate to the sentiment which was also present during the present talk, and that is that if there was a way to not use neural networks, I would absolutely use that option. But unfortunately, in some cases, they're so useful that it is just hard to ignore. So what is the spatial statistics about? This is really a very old field. You might be really surprised to learn that the first map of a disease was made in 1691. Of course, maybe there were other disease maps, but this is the first map that we have access to. And that was the map of containment areas in Italy. So military structures in Italy back in the day decided, oh, this is the way how we fight outbreaks, how we fight diseases. We subdivide the entire area into regions and then implement interventions at this level. Of course, the famous Jon Snow map. Who knows who's Jon Snow? The winter is coming. The other Jon Snow? Yes, another Jon Snow. Not far from here, so back in the UK, this is where the entire domain of disease mapping was actually born, thanks to Jon Snow, who mapped all cholera cases on the map, and that's how we realized that cholera was a waterborne disease. I come from Oxford, and of course, very proudly can say this is one of the high-quality maps that we have access to, which for the first time was able to show in very high detail, at very high resolution, again, the distribution of cholera. And pretty much the history of medicine can be described entirely in maps. The field of research that looks into it is called, I think, social medicine. But in reality, this is actually just a cartography of diseases. And what we will do today, we will discuss a little bit how can we become the Jon Snow of today, because we need to be making those maps, but of course we want to be using modern tools. And well, guess what? Of course we will do it using Gaussian processes. So the modern methods. This is a GPSS event. So as you might have guessed, Gaussian processes is the driving model in this entire field. However, since 2014, deep learning has become really hard to ignore, and today we will see what can it do for us, for modern day Jon Snows. Let's talk about spatial data. There's only 3 types of it. Again, it might come as a surprise, but I ask you when you go home today, there'll be 1,000 things you want to think about. I know generative models and maybe your practicals and everything Vincent showed you today. But in a spare minute, just try and ask this question to yourself. Can I come up with another type of spatial data? So I will show you 3 types now. Try come up with one other. So this is the first type. It's called aerial data. What does it mean? It means that entire study domain is subdivided into sub-areas. So as you can see, it looks like a patchwork of domains. And then we model processes which are constant over each small subdomain, over each area. Hence, it's called aerial data. So when do we start dealing with such data? When the model, the outcome, the variable of interest is reported at the aggregated level. So this is a map, I think, yeah, it's vaccinations at county level. Not so long ago, we saw a lot of maps also of the UK where numbers were recorded at LTLA level. That is first type of data. Second type of data is geostatistical data. You've probably heard of kriging many times in the last 2 days. This is where kriging was born. This is geostatistics. How does geostatistics work? There are some points in space where we do have observations, and the task is to predict the variable of interest in the observations that we don't observe. So in the contrast to the first type of data, we go now from piecewise constant surface to a surface that is continuous in space. Here's a third type of data, point pattern. Again, it consists out of points that we observe, and the task is to reconstruct a continuous surface over the domain of interest. So you might ask, what's the difference with the previous one? So the difference is that the points in geostatistical data are those where we chose to sample, where we chose to collect observations. And here, the points themselves are the data, so the locations themselves are the data. And even though those 3 types of data might look different from each other, the underlying model that we use for all of them is the same. Well, I will show you in a moment how modeling procedures differ. However, it all boils down to Gaussian processes. And we model Gaussian processes using hierarchical Bayesian methods. So in summary, you can start thinking about everything I'll show later just as this one big model. So there's some observation, Y. Referring back to the aerial data, think about counts. So for each area in space, we have collected number of persons which are infected with a certain disease. Then there is the observational model, depending on what data we want to model and that we observe. Is it count data? Is it fractions, proportions? Which is the appropriate likelihood? And then in the latent, on the linear level, we construct a linear predictor, and that consists out of 2 parts, the so-called fixed effects. These are all the covariates we can go and measure in the world, and we observe them. And that would just give the familiar regression part. And there's the second part, which is called the random effect. And of course, it is modeled using Gaussian processes. So why do we use Gaussian processes here? We're trying to capture a variation in space which we are unable to describe with fixed effects, so with the covariates that we know and have access to. And the Gaussian process is governed by its own hyperparameters. Another important remark to make, so I said we're going to do it in a hierarchical way, in a Bayesian way. You saw this morning some approaches to approximate inference. How can we do approximate inference? And in the field of disease modeling, this is a very established culture to use Markov chain Monte Carlo. Approximations are fine as long as they work. But as you saw today, they don't always work, they don't necessarily work, and you need, so it's not out of the box. I can use the approximation and trust it. And when it comes to making really important decisions, such as introducing lockdowns, you don't want to be locked in your own house just because someone applied Laplace approximation. I didn't know how to implement the model, right? So this is one of, there's a range of reasons why we want to use Markov chain Monte Carlo. But roughly speaking, perhaps because we can trust it to a large extent that then we can trust approximate methods. And as practitioners, we also don't want to write Markov chain Monte Carlo by hand. Rather, we use probabilistic programming languages. What do they allow us to do? Well, we need to be able to formulate the model, formulate the likelihood, formulate the prior, and then literally press the inference button because there's an engine that someone wrote for us. What are the options out there in the world? There's plenty. The one tested in battle is Stan. PyMC is also a very serious rivalry to that. Pyro, Turing.gl, I'll talk about Pyro in particular a little bit later again. So yeah, here are the modern options. I already mentioned that we want to be using both Markov chain Monte Carlo, but also deep generative modeling. So we need to be able to write down a neural network architecture and train it as well, and then use that architecture within a model run using Markov chain Monte Carlo, within a probabilistic programming language. So when it comes to software, of course you can say, well, do your neural network in the software of choice, whatever neural network framework you prefer. And then, of course, you can re-implement it by hand because you know the architecture and run it within your favorite PPL. Fair enough, however, that's a lot of work, and such a process is prone to mistake. Hence, we would like to pick a couple of a probabilistic programming language and a neural network framework which are able to work together. So Stan and PyMC both do not have such capabilities. However, PyMC just had a new release, so please take my statement with a pinch of salt. I don't know. Maybe now the new release will allow us to do that too. So Pyro and PyTorch is great and immediately obvious choice. However, they're incredibly slow. So on top of Pyro came NumPyro, which works exactly like Pyro, but is much faster, lives on top of JAX. Hence, we can use this couple, and this will be the pair of choice for this type of work. Okay, what is important when we look at results? It's important that, first of all, the clock time is, the wall time is really short. Again, before COVID, probably this was not so much of a concern, and there was no general demand in disease modeling to run models really, really quickly. For example, as I mentioned, in the past, I used to build spatial models, and they would take 2 weeks. You would write your model in Stan, and then 2 weeks later, you'll come back, look at results. Oh, it didn't converge, and then you re-implement it and run it again, and it didn't converge again. And it's fine because you have 4 years to do your PhD. However, the last 2 years have highlighted to us, actually in the situation of an ongoing pandemic, it's incredibly important to be able to update your models quickly. So previous tools don't work. We need new tools. We want them to be fast. Also, we want them to be ideally more efficient. So we don't want to run models fast just because they're fast, but we are unable to say anything about the quality and the results of MCMC. So we also want the results to be very efficient. Okay, so in this entire story, what is the role of Gaussian processes? I think we are not going to look at the slide for too long. You are here for 4 days, and I think you've already seen the definition of Gaussian process probably 5 or 6 times. Back to modeling of aerial data. One more remark is that I will interchangeably now use terms Gaussian process and multivariate normal distribution. Because when we talk about real-life data here, all evaluations will always be happening on a fixed spatial structure or on a fixed collection of points. Hence, from the definition of the Gaussian process, that will be a multivariate normal distribution. So modeling aerial data, what is the idea behind it? And the idea is that we want to be borrowing strength. In the case of continuous Gaussian process, again, this morning and probably yesterday, you saw a lot of cartoon illustrations of how that might look like. So what do we do with piecewise surfaces? We still want to be able to capture this effect that measurements or objects that are closer in space are more correlated than locations that are further away in space from each other. And that is the idea of borrowing strength from neighbors. There is a whole bunch of models of aerial data, but as you can see, they all boil down to be expressed as a multivariate normal distribution. The only difference is in the exact form of the precision matrix, same as Gaussian process and kernels. You choose a kernel, then you construct the covariance matrix, you draw realizations. Same idea here. Modeling point pattern data, so that is the third type of data that consisted out of random points. As you can see, the model is incredibly different. There are suddenly integrals and exponents, but then again, still at the linear predictor level, there's this term, x transpose beta plus f of s, where f of s is again a Gaussian process. So we need to be able to model Gaussian process and apply certain transformations in order to construct likelihood. But the only term that's actually difficult here is still the Gaussian process. So Vincent told you today about approximate methods. And as a preview, I'm going to show you one more. The problem that it solves is, of course, the scalability of Gaussian processes. And there is an additional burden now that we don't want to just be dealing with Gaussian processes themselves. We also want to run MCMC to infer the parameters and hyperparameters. So at every single iteration, our complexity is n cubed. And the rest of the talk has 3 chapters. I'd say if you had to choose which chapter to pay attention to, focus on chapter 1. This is now. What are we going to do? I will show you an approximate method that solves the problem of scalability. I'm not going to claim whether it's better or worse than what Vincent showed you today. It's just another one. Back to the applied problem. As we said, there's various models, all sort of likelihoods, none of them Gaussian. So if you looked yesterday at Gaussian priors, Gaussian likelihood, this never happens in real life. Well, I don't know, maybe to someone it does, but as many models as I've constructed in my life, Gaussian likelihood has never, ever, ever popped up. On their linear predictor level, fixed effect, no problems with that. Random effect, Gaussian process. What do we want to do? We want to get rid of this last term, and we want to substitute it with some other quantity that at inference stage behaves better than Gaussian process. What does it mean it behaves better? Well, it's faster, it's easier to make inference for. And one possible solution is that this new quantity is the decoder of a variational autoencoder. So as you can see, we replaced FGP here with FVAE, and I will explain in a moment where it comes from. Variational autoencoders also have been mentioned today many times. This is how they look like. What's important, that they have a bottleneck layer which has lower number of components than their input data. So if our input data has n components and they are realizations of the Gaussian process on the spatial structure of interest, so we start from n input variables and we squeeze them into the bottleneck layer, which has dimensions, say, d. And what else is important is the structure of this bottleneck layer. So we assume that it comes from a certain distribution that is fairly simple. Here we assume it's standard normal, very important. So we went from correlated n variables to de-uncorrelated random variables. And this is the whole workflow. This is how the whole solution works. So we start by fixing the spatial structure. Recall those pictures where I said there's 3 types of spatial data. So for the first case, when it's just patchwork data, you don't need to imagine anything. The spatial structure is there. It's just fixed. So it's literally for each area, we generate one component of this random vector that we're encoding. Then when we are dealing with just statistical data, point pattern data, there are different ways to go about it, but we need to introduce the artificial computational grid. And how do we do it? Well, we can just say, okay, here's a regular grid. We cover the domain of interest with this grid, and then we generate realizations on that grid. That is the first step. We're fixing the spatial structure. The second step is that on the spatial structure, we start drawing priors. No data here. We don't know what the likelihood is. We just know that over the spatial structure, we can construct a Gaussian process. And we can generate as many draws of the Gaussian process as we want. And what's very important, they're absolutely noise-free. Again, there's no real data yet in place. And we use those draws as data. So we show those draws to the variational autoencoder. What do we get? So we get the variational autoencoder that is trained on the samples from the Gaussian process, which implies that this variational the decoder is able to start with a variable that is normal IIDs, very small dimensionality, pass it through a deterministic transformation, which is the trained decoder, and create a reconstruction which looks, hopefully, like a draw from the Gaussian process that we did fit as data. This is roughly then at inference how we use it. Well, it's called pseudocode. It's not pseudocode. It's a real code in NumPyro. So what is happening here? This is the case where the neural network is re-implemented by hand. So say we have performed the first step. We have trained the neural network, showed a lot of GP draws to neural network. It learned how to create reconstructions. So at inference stage now, in the second function, all we need to draw from the standard normal of a lower dimensionality, then pass it through a deterministic transformation. So there is no cost to MCMC to do that. And in NumPyro in particular, it's very visible because when we make the sample statement, this means that this is the parameter that we want MCMC to infer. And when we say deterministic, well, there's nothing for MCMC to do. Really, there's no cost to MCMC in this line. Great. So why is this a good idea? Why does it work at all? Let's go back to the original Gaussian process. So in practice, how usually would we perform this modeling? We also start in one of the ways to parameterize a Gaussian process, right? We can also start with a standard normal. However, it has the same dimensionality as the input data, n. Then we would calculate the Cholesky decomposition of the covariance matrix. Have you looked at Cholesky decomposition yesterday, maybe? Yes, no? Does it make sense at all? Cholesky decomposition? No? To one person, well, who is overqualified to answer this question. So the idea, you definitely saw covariance matrices, right? So one way to generate samples from a Gaussian process is to say, okay, I sample from normal distribution, which has parameters mu. Okay, let's write this down. Where? No, it doesn't work. Okay, so I'll try right here. So first way to parameterize it, let's say that I sample f from multivariate normal distribution with min mu. Great, thank you. I'll just write normal, you know that it's multivariate normal, mu and covariance sigma, where sigma is calculated from here. Another way to say that I sample from a Gaussian process is to say, actually, mu is a constant, and then I use the matrix L, which is the Cholesky factor, and then we multiply it by a standard normal. So again, this is a variable that is incredibly simple to sample from, and Cholesky L transposed L gives the covariance matrix. So there are two different ways to parameterize Gaussian processes, and when we work with probabilistic programming, it's very important always to check for one or another type of model what is the most favorable parameterization. So the second one is frequently preferred. So mu is not very important. We can forget about it, say this is 0, this is 0. So what's written there basically is this expression that we draw from a standard normal, which has dimensionality n. We multiply it by Cholesky factor. And as you can notice, the Cholesky factor came from the covariance matrix sigma, and matrix sigma had hyperparameters stitched into it. So this guy here doesn't have hyperparameters, but it should. So say it depends on parameter theta, which is something maybe variance here and length scale here. And those hyperparameters make our life very hard when we want to infer them. And in practice, of course, we always want to infer them. So what have we gained? This approach on the left, the traditional one, has cubic complexity. Now, we also start on the right-hand side. We also start with a standard normal variable. However, instead of passing it through this, well, even though a linear operation of multiplying it with a Cholesky factor, but that Cholesky factor does have hyperparameters in it, so MCMC is doing work on it. So instead of that, we apply the deterministic transformation phi, which uses weights W, which are fixed. They're just numbers. Okay? So in reality, the complexity now went from cubic to something that's of order d times n, where you can see that if d is very small compared to n, it's close to linear even, so it's nearly O of n. Well, if d is high and nearly n, then, well, it becomes n squared. These are some of the first results. What do we see here? The behavior that we expect from Gaussian processes is that when we start observing data, the uncertainty intervals shrink around the areas where there is data, and they're wider in the areas where there is no data. And as you can see, the behavior of this model is very close to that. Also, you might say, okay, what about the aerial data that we started talking about? Again, we can use those models here too, and they are not reliant on those continuous kernels. But in exact same way, since this is just a multivariate normal distribution, in exact same way, we generate random vectors, use them as data, and we can perform the usual disease mapping task. So what is the task here? I have not explained. Well, we want to model HIV prevalence in Zimbabwe, and there's some observed data here. What disease mapping aims to do, so we want to borrow from neighbors, and when we see a map like a patchwork on the left, which has suddenly very high values in one areas and much lower values in other areas, we don't necessarily trust it, and the problem is called the small area estimation. Because some areas are so small, there is very little data. For statistical reasons, it is unreasonable to use the raw data. Hence, we want to borrow strength from neighbors. This is what these models are doing. So as you can see, just the clock time, the elapsed time, is lower. But most importantly, the model is also more efficient in the sense that so-called effective sample size is higher. That is a similar example applied more closer to home, also a country with a much higher number of areas for which we want to perform modeling. So in summary, there was chapter 1. So now was the time to pay attention. If you didn't, now still last slide to pay attention to. What was great about this approach? So we substituted something incredibly correlated and hard to make inference for with something uncorrelated and very easy to deal with within MCMC. Something I have not mentioned yet is another feature that because data is not actually real data but just draws from priors, both the amount of this data is unlimited. The data is noiseless. And on top of that, we don't need to store all of this data in one data set. Of course, we can. There are two approaches. We can generate all the samples, store them in one data, and then do batch learning over the data set. However, we can equally generate batches on the fly. The efficiency of MCMC inference has been shown by the effective sample size. There are certain disadvantages, of course, as well. I mean, the main disadvantage, it's an approximation, okay? But going back to this morning, you saw some other methods, they also approximate. It's really hard to do anything exact in this context when our likelihood is not Gaussian. Another drawback of this method is it is not able to predict off-grid because if you can recall, the first step of the procedure is we're fixing the spatial structure. So anything that was not a part of the spatial structure from the start, we won't be able to say anything about. If you would like to take a look or play with the code for this model, it's publicly available. Okay, second chapter is more of an application of the first one. Okay, we now know how to encode random vectors. We're able to make maps, in particular of aerial data, really efficiently, really quickly. What else can we do? Well, there's a range of things. Now, because the draws of the Gaussian process are so cheap, we can do anything that requires transformations of those Gaussian processes. We can aggregate, we can take max, mean values, or any other operation. So here's a very quick snapshot of, for example, how aggregation might work. This is a real-life problem from Kenya. Kenya happened to change boundaries in 2010. Imagine for a disease surveillance program where they want to track the progress of their work before 2010 and after 2010. It's virtually impossible because you can't overlay spatial units. Well, what to do? Well, you use priv-AE, aggregate it, you get agv-AE, and call it a day. So there's an additional problem as well with those adjacency-based models, and it's that they assume heterogeneity. When we model Gaussian processes with continuous kernels, well, there is an understanding that at every point in space, the value of the output variable y will be slightly different, right? And even though we might not be able to measure it directly, even though we don't have access to those variables, still it's healthier to understand there is something going on in space, but perhaps we just want to report it in a manner that's accessible to us. So adjacency-based models only take into account the adjacency structure, meaning who is neighbor with who. And there's no notion where the area is large, small, or what's the population. So for example, is London is neighbors with some other small area where there is no population. Oh, well, I guess from London it evolves continuously in space. But imagine if there are two countries like North Korea, South Korea, all you know is just who is neighbor with who. You don't know what's happening within each of the areas. Very unreasonable. And yeah, the obvious second problem here is the change of support, and that is the change of boundaries. Okay. that's not the aerial problem anymore because we choose to reframe it using continuous kernels. So we introduce our own spatial structure, an artificial grid that is regular. Then we draw those evaluations of the Gaussian process. So here's your sigma covariance matrix that we spoke about. And we can do this for both old map and the new map because, okay, well, this spatial grid is deliberate. So we aggregate the values to any level that we want. And then we can stack those two vectors. So aggregates from the first, aggregates from the second. This is one joint vector. And we can use them jointly now with the same prive technique. So that's a cluttered slide, but actually it's very similar to what we saw before, the summary of the prive method. It just has a couple more methods to create that data that we pass to the prive. So let's walk through it again. We start with fixing of the spatial structure. In the first case, so if it was aerial data, the spatial structure is given. Here we choose to introduce the computational artificial grid. Then we draw evaluations of the Gaussian process over the artificial grid, remember? So we're getting rid of the notion who is neighbors with who. We'd rather say we believe that the process is continuous in space, and the notion of neighborhood comes just from the aggregation step. And then we jointly encode that very long vector, aggregates over old boundaries, aggregates over new boundaries. And now, after the VE has been trained, we can again use as plug and play this new quantity at inference stage within MCMC. What are we modeling here? The applied problem here is to map malaria prevalence in Kenya. What data is available to us? So at every aerial unit, we have collected number of tests which were performed, and we know what was the number of positive tests. So, and the prevalence in this case is the probability of a test to be positive. As you can see, there are two models now. So one, when we say, okay, what if we still worked with the original Gaussian process? How would that model look like? Okay, we would draw Gaussian process evaluations over the grid. We would aggregate, perform the aggregation step, then calculate the joint vector, then plug it into the likelihood. And as you can see, this would take us 15 hours, even more. So after 15 hours, this model did not even converge. However, when we use our new tool, it takes only 5 seconds. So nothing new is in this approach. So the idea is still the same as it's the one of prive. This was an example of how it can be applied to problems which look really hard. Okay, so this is now chapter 3, to say so. If you fell asleep during the chapter 2, now it's time to wake up again because it's getting exciting. So what is exciting about this piece? Recall in prive we use the draws from the Gaussian process. And Gaussian process draws came from a certain covariance matrix, which had hyperparameters. When we only show evaluations of the Gaussian process to the VE, we are not telling anything to the VE about the hyperparameters, right? So if the length scale is short, we might get a very wiggly evaluation. If the length scale is long, we might get evaluations which look nearly like a straight line. But VE has no notion of it. So what on earth has it learned? And most importantly, if we need to infer length scale, and in practice for disease mapping, that would mean like, at what range is the distribution of this disease working? So isn't it important if I introduce the lockdown here, do I actually also have to introduce a lockdown in lung cluster, or if I have a disease here, is the length scale so long, I actually have to introduce a lockdown in London. So what can we do for that? And the answer is, it's just a little tweak to the architecture. So from the variational autoencoder, we go to conditional variational autoencoder, which means that alongside the realization, the random vector itself, we also pass the values of the hyperparameters that it was generated from. So think in case of one hyperparameter length scale, so we pass the realizations, we say, here's the very, very wiggly curve, and it came from this very short length scale. Or here's this non-wiggly curve, and here's the value of the length scale. And as a result, both we hope to get better reconstruction. So we should be able to obtain draws by using the decoder, which correspond to different length scales as well. And second benefit of this approach is that now we would be able to infer the values of hyperparameters within MCMC. So here's a couple of examples. These are just priors. There's no data, no inference here yet. So the top two plots are extreme cases of Gaussian process draws. So the one on the left is with length scale 0.2, the one on the right with a length scale 0.9. Then the second row, so we use exact same data and pass now to two different models. The PriVAE, the first one, which looked absolutely amazing at the first glance, right? And then we see what draws we're able to reconstruct. So as you can see, the two plots in the middle line actually are absolutely insensitive to the value of the length scale. Well, they do reconstruct something. They do produce curves, which look like Gaussian process, right? They're continuous, they have some amount of wiggle, but there's no notion of range. At what range should that wiggle happen? And now the bottom line is the new model, the conditional variational autoencoder. And as you can tell, there is very good reconstruction with regard to the length scale. Another surprising fact which comes out of the box, so I think earlier today we heard about the fact that you need to do a lot of tweaking for neural networks. Yes, you might. However, sometimes things just don't require any extra effort. And here's two amazing facts about this approach, which were just out of the box. So here on the blackboard, I saw you had a kernel which is stationary. Everything I showed to you so far also only had stationary kernels. So how about non-stationary kernels? And here's an example. These are plots of the kernel that is the product of RBF and linear. So makes this butterfly shape. And surprisingly, the method works for them too. Furthermore, the method also works with respect to extrapolation of hyperparameters. What does it mean? So if at the training phase we pass values of hyperparameters from a certain range, here, for example, it was from 0 pretty much up till 0.4, and you say, well, you gave me this pre-trained model, which was trained on these length scales, but what if what I need are the draws from length scale 0.5? Right? What a limitation. Well, it turns out that at no cost we can draw such reconstructions too, and of course, as you might expect, the quality of reconstruction decays the further that value we want to extrapolate for is from the original values that VAE was trained on. A little remark again on other approximate methods. Laplace is a wonderful idea, very hard to do by hand, and again, we live here in the world of probabilistic programming. Say, I'm an applied scientist, I'm not spending 4 years now creating my own Laplace implementation or any other, say, MCMC scheme. I want to be able to use the same PPL, probabilistic programming language, to do exact same inference. Can I use other approximations? Well, possibly, but these are the results that I got out of NumPyro. They don't make much sense, to tell you honestly. So what's on the left is the result of NUTS, an MCMC scheme. That's what we want to use. If in NumPyro you use Laplace, so for some reason uncertainty collapses just to the mean, and ADVI gives a result which I'm not even going to comment on. Okay, let's go. So there are two contestants now. There was prior VIE and prior CVIE. So how do they behave once we start seeing the data? First of all, it comes by definition. Prior VIE is not able to infer hyperparameter at all. So the tiny little plot on the right, which shows prior and two posteriors of the hyperparameter, does not even have a line for prior VIE. Prior VIE is not capable of doing such work. What are we comparing then? The posterior of the hyperparameter of the original model and the prior CVIE model. So visually, as you can see, they're quite close. And then also at inference, the uncertainty bounds that are reconstructed by prior CVIE are much closer to the original model than the prior VIE. In terms of just dwell time, prior CVIE is slightly worse. Well, it does have an extra parameter, right? And it generally provides, so it makes much better reconstruction. So in that sense, we're not losing much, because still at the level of effective sample size per second, the result is still about 10,000 higher than with the original GP model. So what I just described now is covered in the three, one published work, one workshop paper, and one preprint. What's next, you might ask? So I might have been able to convince you that the method works. It does work to some extent, but of course it's not perfect. And there was the first, so going from prior VIE to prior CVIE was the first attempt to improve their reconstruction. However, the sky is the limit of what can be done and how well those reconstructions can be. So far, the ways to evaluate the quality of the reconstructions were either visual inspection, then looking at empirical covariance matrices like here. So what do we see here? This is the non-stationary kernel example that, as I said, worked out of the box, was probably one of the most impressive observations in this work so far. Okay, for more or less average length scale and very short length scale, visually they don't differ much. But then when you start exploring their uncertainty bounds for prior VIE itself, they do not match the original ones very well. Then prior CVIE is a good step forward, however, still not perfect, and there's a lot of work to be done. The method is there overall, and I showed you one also methodological application. There was change of support problem. Now there's some exciting, really applied work done by Prakhar, who is in this room. He works on the domain of population genetics. Also, there's a lot of room for using different geometries. So we heard today how important is geometry. And disease mapping, for as long as it existed, Euclidean space was pretty much all there is. And we used to make maps of small areas. So if you assume UK is flat, that's more or less okay. But when you start modeling sub-Saharan Africa or the entire globe and think that this is a flat area, then your modeling might not be very precise. So what needs to happen also is capturing of geometry, be this more continuous structures such as spheres or semispheres and such, or perhaps also network structure. Related work I have not mentioned, and very important, is mostly a PyVAE method. So what's it about? Remember I said that PyVAE has one drawback, is that we are unable to make predictions off-grid. In the area where I work, and that is small area estimation, this is not a problem at all because, well, if we work on small area estimation, the areas are defined because we already know these areas are small, these areas are large. So it's not a limitation actually. But if what we want to do does require prediction of grid, such as kriging, for example, then it is very valuable to predict off-grid. And PyVAE existed before PyVAE did. It was just not very legible. So PyVAE was an attempt to make a step back and say, okay, let's not look at learning Gaussian process as functions. Let's just try to learn random vectors, and then results of PyVAE fed back into PyVAE work, and you can find the publication online also. Fascinating read. Another application of PyVAE, which I have nothing to do with, which means it actually works, so someone else is able to use it. And there was modeling of Hawk's processes. So Hawk's process is a branching process where part of it does use Gaussian process realizations. And GPs themselves computationally are not trivial, as you might have noticed. And Hawk's has even more complications on top. So this is a case where PyVAE was able to alleviate difficulties with another model. So all this work is incredibly young, very new, and you can contribute, you can try, you can criticize. Here's a bit of a historical overview of software, where and how it existed. So the first version, PyVAE, it's online, you can try it, you can run it. It's ugly, not just because the code itself is ugly, but also the choices were a little bit ugly because they used existing NumPy way of dealing with variational inference. So if you want to try PyVAE, this is a good start because it follows exactly the workflow that I showed you. However, if you want to work with something more legible, and also PyVAE is now so 2022, we need to move forward. There is a newer version, still pretty terrible code that was in PyTorch. Again, it works. It demonstrates what it has. And the Colab in it has those empirical diagnostic measures. So remember I said, how are we currently evaluating the quality? Well, visually and empirically. And exciting new development is now porting of all that work to JAX to make things faster. Remember I said NumPy works well with JAX, so why on earth do we need PyTorch? Because then someone has to go manually re-implement the entire architecture. Again, Prakhar in this room is working hard on the JAX version. And if you would like to try the method in its new form, this is definitely the place to start. So a lot of ways to contribute. If you have any ideas, suggestions, or just would like to try things out, please reach out, or don't even reach out, just take one of those links and try them for yourself. This work has been done and is still happening with a lot of collaborators. It is inspired by very applied work. Hence, you can see we do have a lot of collaborators from Imperial College London, now from University of Bristol and National University of Singapore and Copenhagen. So all of these people sit somewhere on the spectrum from being very applied to living in the machine learning world. If you want to see your name on the slide one day, also the slide still has a lot of space, and I can always reduce the font to squeeze more names in. That is it about this type of work. Open to questions now or pretty much any time in the future. Questions?